In this session, let us solve a numerical problem on the three-phased ground fault. We have a generator connected to a transformer. The rating of the generator are given. Three reactance values are given for this generator. This is the subtransient reactance marked as XD double dash. This is the transient reactance marked as XD dash. This is the steady state reactance of the generator marked as XD. As soon as the fault occurs in the system, in the first few cycles, the reactance of the generator is at the least value, and obviously the fault currents will be at the highest magnitude, and this time period is called the subtransient time period of the fault analysis, and the fault current in this period is called the subtransient fault current. After this period, the reactance is increased to comparatively a higher magnitude. Obviously, the current is reduced to a lesser value, and this time period is called the transient period, and the fault current in this period is called the transient fault current. After this transient period, the reactance of the generator is increased to a higher magnitude, and the current is reduced to a lower value, and it is settled down at a steady state fault current. In the case of fault analysis, the subtransient period is the most important one, because in the subtransient period, the reactance is having the least value and the fault current is having the highest magnitude. So now question, we need to find out the initial symmetrical current on both high tension side and the low tension side of the transformer. As we have to find out the initial current, we need to consider only the subtransient period, or we have to consider only the subtransient reactance. We need not to consider the transient reactance or the steady state reactance of this generator. Let me draw the reactance diagram. Let me draw the single line diagram of this power system. We have a generator and a transformer. The fault occurs on the high tension side of the transformer. The rating of the generator is 100 MVA, 18 kilovolt. The reactance is 19%. The transformer rating is 100 MVA. Its voltage rating is 240 bar 18 kilovolt. But the primary of this transformer is connected to the generator with a rating of 18 kilovolt. So this transformer should be connected as 18 bar 240 kilovolt. Its reactance is 10%. The delta is on the 18 kilovolt side. So this is delta star transformer. This 19% reactance is same as J 0.19 per unit. This 10% reactance is same as J 0.1 per unit. Now, this reactance is given with a base of the rating of this transformer. And this reactance is given with a base of the rating of the generator. So the reactance values, the per unit reactances are given with a different base values. We have to find out the per unit reactances on a common base value. Let us choose the generator rating as the new base values. So MVAB new equals 100 MVA. KVB new equals 18 kilovolt. So the rating of the generator are chosen as the new base values. Now the MVA base new equals 100 MVA and KVB new equals 18 kilovolt. Now throughout this power system, the MVA base will be 100. But when you move from one side to the other side of a transformer, the voltage will change. So this KVB new will change. Now let us find out what is the KVB new on the high tension side of the transformer. The KVB new on HT side is equal to KVB new on LT side into the transformer ratio HT divided by LT. What is the KVB new on LT side? On the low tension side it is 18 kilovolt. The transformer ratio is 240 by 18. And this is equal to 240 kilovolt. So this is the KVB new on the high tension side of the transformer. Throughout this power system, MVA new will be 100 MVA. When the voltage increases, obviously the base currents will reduce. After choosing the base values, we have to draw the reactance diagram. Then we have to mark the per unit reactances. Then we have to find out the Thevenin's equivalent circuit at the fault point. Then we have to find out the fault current. This is the approach we are using to solve the three-phase ground fault problems. So next step is to draw the reactance diagram. Let me draw the reactance diagram of this power system. We have a generator. This is the reactance diagram of the generator, a voltage source and a reactance. Then the transformer. Now this voltage will be equal to the per unit voltage of the generator equals the actual voltage of the generator divided by the base kilovolt on the generator side. This is also 18. So this is 1 angle 0. Now let us find out the reactances on a common base value. Let us start with the generator, the reactance of generator. This is the formula we are using to convert the per unit reactances in one base to another base. X per unit new is equal to X per unit old into KVB old divided by KVB new the whole square into MVAB new divided by MVAB old. The X per unit old is given with the base of its own rating. We have to convert this X per unit old into X per unit new with the new base values. These are the new base values. These are the old base values. Old base values are same as the rating of the equipment. Now the generator rating are chosen as the new base values. So X per unit old and X per unit new will be same for the generator. This is equal to J 0.19 per unit. Let me mark the value here, J 0.19 per unit. Now let us find out the reactance of the transformer. The per unit reactance of the transformer can be found out either on the primary side or on the secondary side. The per unit reactance will be same on both sides for a transformer. Let us find out the per unit reactance on the primary side. The X per unit old is J0.1 into kVb old on the primary side is 18 kilovolt divided by kVb new on the primary side is also 18. The whole square into MVA based new is 100 MVA. MVAB old of the transformer is 100 MVA. So this is equal to J 0.1 per unit. Let me mark the value here. So this is the reactance diagram with all per unit reactances. This is the fault point because the fault occurs on the high tension side of the transformer. Our next step is to draw the Thevenin's equivalent circuit at this fault point. The Thevenin's equivalent circuit consists of a voltage source in series with the Thevenin's equivalent reactance. This is the Thevenin's impedance or the Thevenin's equivalent reactance. This is the Thevenin's voltage source. This is the voltage available at the fault point before the occurrence of fault. Before the fault, it was at the no load condition, so no current was flowing through the circuit. So there is no voltage drop across these reactances. So this voltage will be available at this fault point before the occurrence of fault. So this is 1 angle 0 per unit. ZTH is the per unit reactance at the fault point. It is J0.19 plus J0.1. It is J0.29. Now we got the Thevenin's equivalent circuit. Now let us apply the fault condition. So this is the fault. So let me mark this as IF double dash. This is the subtransient fault current because we have considered the subtransient reactance, the reactance at the initial portion, the initial time period after the fault occurs. Now what is the fault current flowing through this circuit? The total voltage divided by the total impedance. So IF double dash per unit is equal to, it is IF double dash per unit, VTH divided by ZTH. This is 1 angle 0 divided by the reactance is J 0.29 and this is equal to 3.44 angle minus 90 degree per unit. When you consider this circuit, this is the fault point, this is our transformer reactance. On both sides of the transformer, the per unit current is same because this is a series circuit. So the per unit reactance, the fault current on the high tension side of the transformer is 3.44 angle minus 90 degree. On the low tension side also, the per unit fault current is same. It is 3.44 angle minus 90 degree. But the actual fault currents will be different on the high tension side and on the low tension side. How will you find out the actual fault current? The per unit fault current into the base current on that side. Now let us find out the base current on the high tension side. IB new on HT side. This is equal to MVAB new into 10 raised to 3 divided by root 3 into kVb new. And this is equal to the MVAB new on the high tension side is 100 MVA divided by root 3 into kVb new on the high tension side is 240 kV. And this is equal to 240.56 amperes. Now let us find out the IB new, the base current on the LT side, on the low tension side. This is equal to MVAB new on the low tension side is 100 MVA into 10 raised to 3 divided by root 3 into KVB new on the low tension side is 18 kilovolt. So this is equal to 3207.5 amperes. Now we got the base currents on both sides of the transformer. Per unit current is same on both sides. Now let us find out the actual fault current. IF double dash on the HT side. This is equal to the per unit current into the base current. IB new on HT side. This is equal to the per unit current is 3.44 angle minus 90 into on the high tension side the base current is 240.56. So this is equal to 827.5 angle minus 90 degree amperes. The fault current on the LT side is equal to the per unit fault current into this IB new on LT side. The per unit current is same on both the sides of the transformer. It is 3.44 angle minus 90 into here the base current on the low tension side is 3207.5 and this is equal to 11033.8 angle minus 90 degree amperes. So this is the subtransient fault current on both sides of the transformer, on the HT side and on the LT side.